Our universe is a place of profound mysteries. From the smallest particles to the largest galaxies, the cosmos holds secrets that have captivated humanity for millennia. Among the most intriguing and perplexing of these is the realm of quantum mechanics. This strange and counterintuitive world, where the very fabric of reality seems to bend and twist, challenges our everyday understanding of how things work. Paradoxes have always held a special allure for the human mind. They represent puzzles that seem to defy logic, forcing us to question our assumptions and seek new ways of understanding. In the realm of quantum mechanics, paradoxes take on an even deeper significance. They serve not only as intellectual curiosities, but as profound clues to the true nature of reality. Imagine a bomb so sensitive that the slightest touch could set it off. Now imagine a collection of these bombs, some live and ready to explode, others duds, harmless and inert. Your task: identify the live bombs without detonating them. This is the intriguing premise of the Elitzur Vaidman bomb tester, a thought experiment that highlights the strangeness of quantum mechanics. In the classical world, determining the state of the bombs would be impossible without triggering the live ones. You could try to X-ray them or analyze their composition, but any interaction would risk setting off a chain reaction. The very act of observation, of gaining information, would inherently alter the system, potentially with disastrous consequences. To understand how we can detect the bomb without directly interacting with it, we need to introduce a crucial piece of equipment, the Mach-Zehnder interferometer. This ingenious device, named after its inventors Ludwig Mach and Ludwig Zehnder, is essentially a quantum playground, allowing us to manipulate and observe the strange behavior of light and matter. Imagine the interferometer as a miniature racetrack for photons, the fundamental particles of light. The photons enter the racetrack and are then split into two possible paths, using a beam splitter, a device that reflects some of the light and transmits the rest. This splitting doesn't force the photon to choose one path or the other. Instead, the photon enters a state of superposition, traveling along both paths simultaneously. Section 3, the astonishing outcome: detection without interaction. Here's the truly mind-boggling part. Even if the photon doesn't directly hit the bomb, even if it takes the other path, the mere presence of the bomb in one of the paths is enough to alter the interference pattern. This is because the photon, in its state of superposition, is sensitive to both paths simultaneously. It's as if the photon, like a skilled detective, is able to gather information about the entire racetrack, including the presence of the bomb, without ever setting foot in the bomb's path. This remarkable phenomenon, known as interaction-free measurement, challenges our classical intuition, where information can only be obtained through direct interaction. Embracing the quantum beyond classical intuition. The Elitzur Vaidman bomb tester challenges our classical intuition. In our world, objects have definite properties, like a bomb being live or a dud. But in the quantum world, certainty gives way to probability. Quantum superposition means particles exist in multiple states simultaneously. Section 2, the dance of possibilities, superposition unveiled. In the Elitzur Vaidman bomb tester, the photon entering the interferometer doesn't simply choose one path or the other. It embarks on a journey through both paths simultaneously. It's like a quantum explorer scouting out the terrain, gathering information about both routes, even though it can only physically occupy one at a time. This exploration, this dance of possibilities, is what allows for interaction-free measurement. The photon, in its superimposed state, is sensitive to the entire interferometer, to the presence or absence of the bomb in either path. Even if the photon doesn't directly interact with the bomb's presence casts a quantum shadow, altering the very fabric of possibilities. Section 3. The paradox of measurement. Knowing without touching interaction. Free measurement, the ability to gain information about a system without directly interacting with it, stands as a testament to the strangeness of quantum mechanics. It challenges our classical notions of cause and effect, where information is seen as something that must be extracted through force, through a probe or a sensor. In the quantum world, information is not so much extracted as it is revealed. The act of measurement, of trying to pin down a particle's state, forces the superposition to collapse, forcing the particle to choose one path or the other. But this collapse, this choice, is not predetermined. It's a probabilistic event influenced by the entire quantum landscape. A dance of matter and antimatter. Hardy's paradox explores the bizarre relationship between matter and antimatter. Imagine a dance floor where the partners are an electron and a positron. These particles, identical except for their opposite charges, are drawn to each other. In the classical world, they would annihilate each other in a burst of energy. But in the quantum world, things are never straightforward. The dance takes on a surreal quality, defying our understanding of space and time. Section 2. The paradox unfolds. To be and not to be. Here's where the paradox rears its head. Quantum mechanics tells us there's a non-zero probability that both the electron and the positron will be detected at the end of their interferometers seemingly unscathed. It's as if the dancers, despite their overlapping paths, have somehow managed to avoid each other, their annihilation averted. Section 3. The implications, a universe redefined. Hardy's paradox is not merely a theoretical curiosity, a mind-bending puzzle for physicists to ponder. It has profound implications for our understanding of the universe and our place within it. It challenges us to reconsider our notions of determinism, the idea that the present dictates the future, and to embrace a world where chance and probability reign supreme. The paradox also highlights the non-local nature of quantum mechanics, the idea that particles can be connected in ways that transcend our classical notions of space and time. The electron and positron in Hardy's paradox seem to know about each other, their fates intertwined even though they may be separated by vast distances. Section 1. The heart of the paradox logic's crossroads in the quantum maze. Hardy's paradox, with its seemingly contradictory outcomes, strikes at the very core of how we understand the world. Our classical minds, accustomed to the neat cause and effect relationships of everyday life, struggle to grasp a reality where something can be both true and false, where events can both happen and not happen. Yet this is the terrain we find ourselves in when we venture into the quantum realm. The paradox arises from the clash between our classical expectation of a single definite outcome and the quantum reality of a superposition of possibilities. In the classical world, the electron and positron either annihilate upon meeting or they don't. There's no room for ambiguity, no space for both outcomes to be true simultaneously. But the quantum world thrives on ambiguity, on the blurring of boundaries between what is and what could be. Section 2, Beyond Cause and Effect, Embracing Quantum Ambiguity. Hardy's paradox challenges our notion of cause and effect. In the classical world, events are linked predictably. If A happens, then B follows. But in the quantum world, cause and effect blur. The present doesn't dictate the future, and multiple possibilities coexist. The quantum realm invites us to embrace ambiguity. Section 3. Echoes of Annihilation, the persistence of quantum information. Another intriguing aspect of Hardy's paradox is the question of what happens to information during a quantum event. In the classical world, information is generally thought of as being either preserved or destroyed. When a book burns, for example, the information contained within its pages is lost. But in the quantum world, things are not always so clear-cut. The paradox suggests that even when particles annihilate some aspect of their existence, some information about their past might persist. This is because quantum entanglement, the strange link that connects the fates of particles, even across vast distances, suggests that information might not be localized in the same way that matter is. From thought to technology, quantum mysteries at work. The Elitzur Vaidman bomb tester and Hardy's paradox, while deeply rooted in the theoretical realm, are not just abstract puzzles for physicists to ponder. They offer a glimpse into a world of possibilities where the strange and counterintuitive laws of quantum mechanics could be harnessed to create groundbreaking technologies, revolutionizing fields like computing, communication, and cryptography. One of the most promising areas of application is quantum computing. Unlike classical computers, which store information as bits represented by zeros or ones, quantum computers exploit the superposition of quantum bits or qubits. Qubits can exist in a combination of 0 and 1 simultaneously, allowing quantum computers to perform computations exponentially faster than their classical counterparts for certain types of problems. The quantum frontier, exploring the unseen and the unknown. Beyond their technological implications, the Elitzur Vaidman bomb tester and Hardy's paradox also serve as powerful reminders of the vastness of our ignorance. They force us to confront the limits of our classical intuition, to acknowledge that the universe is far stranger, far more wondrous than we could have ever imagined. These paradoxes are not problems to be solved, but rather mysteries to be explored. Invitations to delve deeper into the quantum realm, to unravel the secrets of a reality that operates according to rules that defy our everyday experience. The quantum legacy, a universe transformed. The Elitzur Vaidman bomb tester and Hardy's paradox stand as testaments to the transformative power of quantum mechanics. They are not merely intellectual curiosities, but rather profound insights into the nature of reality, challenging our classical intuitions and revealing a universe far stranger and more wondrous than we could have ever imagined. These paradoxes, with their seemingly impossible outcomes, force us to confront the limits of our everyday experience, to acknowledge that the universe does not always conform to our expectations. They invite us to embrace the unknown, to revel in the ambiguity, to expand our minds to accommodate a reality that operates according to rules that defy our classical understanding. Embracing the enigma, our quantum future. The quantum world is poised to play a significant role in our lives. Quantum technologies are rapidly becoming a reality, revolutionizing fields like medicine, materials science, and AI. The true promise of quantum mechanics lies in transforming our understanding of the universe. It invites us to embrace the interconnectedness of all things and the probabilistic nature of reality. The Elitzur Vaidman bomb tester and Hardy's paradox remind us we are only scratching the surface. As we probe the quantum frontier, we encounter more paradoxes and mysteries. Embrace the unknown, for it reveals the beauty, complexity, and strangeness of our universe.
Sun is shining.